Is a cat still a cat when I'm not looking at it? Can anyone or anything predict our every move? Is it possible for this world to produce a result before its cause? Is the universe deterministic? Does time even exist? If you've ever pondered any of these questions, you have a uniquely wired brain and a natural aptitude for quantum mechanics. Sit tight, because we're going to start with an experiment that seems deceptively mundane but escalates into sheer terror. The double-slit experiment. Back in the 17th century, humanity's understanding of light was largely dictated by Isaac Newton. Newton believed that light was made up of tiny particles. Naturally, some disagreed. Dutch physicist Christian Huygens argued that light was a wave. However, Newton's reputation was so towering that opposing views stood little chance. It wasn't until 1807 that a 34-year-old British scholar named Thomas Young conducted a seemingly simple experiment that would forever change our understanding of light and unleash a profound mystery that still baffles humanity today. Young was a true polymath. He could read by age 2, taught himself Latin at 6, began studying medicine at 19, and was deeply passionate about and proficient in both physics and Egyptology. During his medical studies, Young's fascination with human hearing and vision sparked a keen interest in the physics of sound and light. Though he idolized Newton, he had reservations about the claim that light was purely particulate. He suspected that light propagated much like sound, and the scientific community at the time already knew that sound traveled in waves. Starting in 1801, Young began designing relatively simple experiments, culminating in his famous double-slit experiment in 1807. The setup was straightforward, consisting of 3 parts: light source, barrier with 2 slits cut into it, and a screen to catch the projection. The logic was simple. If light were truly made of particles, would travel straight forward like bullets, facing the double slits. The particles would randomly pass through either the left or the right slit. Behind the barrier, the screen would show 2 bright bands. However, if light were a wave, imagine ripples on water. The light waves passing through the 2 slits would interfere with each other, creating alternating bright and dark stripes on the screen, known as interference fringes. Just as physics textbooks show, the fringes appeared. This proved light was indeed a wave. But later, Albert Einstein proved through the photoelectric effect that Newton wasn't entirely wrong either. Light also behaves as a particle. This left everyone mind-boggled. It wasn't until 1924 that Louis de Broglie proposed the concept of wave-particle duality, suggesting that microscopic particles, including photons, electrons, and protons, possess both wave and particle characteristics simultaneously, finally reconciling the debate. Let's return to the double-slit experiment. Young could never have imagined that a century later, his peers would start heavily modifying his setup, with each iteration yielding increasingly bizarre results. In 1909, British physicist and mathematician Geoffrey Taylor conducted the first major modification. He dialed down the intensity of the light source, ensuring that at most 1 photon passed through the slits at a time. Otherwise, the setup remained identical to Young's original. Photons flew through the slits one by one. Common sense dictates that 2 bright bands should appear on the screen. But to Taylor's astonishment, the interference fringes still appeared. In Young's experiment, we could attribute the fringes to multiple photons interfering with one another. But if photons were fired one by one, why were there still fringes? Did a photon interfere with itself? In fact, that was exactly Taylor's conclusion. The photon interfered with itself. What does this imply? It implies that the photon likely passed through both slits simultaneously. While this is hard to grasp in our macroscopic world, the weirdness was only just beginning. In 1965, legendary physicist Richard Feynman proposed a thought experiment. What if, right before the photon hits the slits, we place a camera or detector to observe exactly which slit it goes through? Feynman predicted that the interference pattern would completely vanish. He argued that for microscopic particles, although both particle and wave natures exist, they cannot be observed simultaneously due to technological limitations. This experiment wasn't actually conducted until the late 1970s. The results were shocking. With the detector off, the interference fringes appeared. No problem there. But the moment the detector was turned on, the interference pattern on the screen vanished entirely, leaving only 2 bright bands. Exactly as Feynman predicted, things were starting to veer into the realm of the occult. Aside from flipping the detector on and off, every single experimental condition remained unchanged. It was as if the particles knew they were being watched. You're watching me? Fine. I'll behave like a particle. Pick 1 slit and land neatly on the screen. You look away? I'll interfere with myself and become a wave. What's it like? It's like hearing my mom's approaching footsteps. before she opens the door. I'm gaming so hard my phone is practically smoking. The exact second she pushes the door open, I transform into a diligent student buried in books. You can't observe my dual nature simultaneously, but you can't deny it exists. In 1979, physicist John Wheeler proposed another thought experiment. It seems geniuses don't even need physical equipment, strictly speaking. This setup differs quite a bit from the classic double-slit experiment and is quite complex, utilizing half-silvered mirrors with a 50% reflectivity and detectors. However, the underlying principle is the same. So for clarity, I'll use the double-slit analogy. Essentially, the question is, if the photon has already passed through the slits, I then randomly decide whether to observe it. Will it still produce an interference pattern? Does the photon have time to change its choice? This is the famous Wheeler's delayed choice experiment in quantum mechanics. By now, you're probably getting the picture. The evolution of the double-slit experiment is basically history of physicists and particles playing an increasingly elaborate game of hide-and-seek. 5 years after Wheeler proposed his thought experiment, several scientists brought it to life. Using our analogy, they placed a detector at a point between the slits and the screen. They didn't turn it on for every trial. After the photon passed the slits, the detector was sometimes suddenly switched on, and sometimes left off. The result? The photons weren't fooled at all. Whenever the detector was on, no interference fringes appeared on the screen. Whenever it was off, the fringes invariably showed up. It was foolproof. This iteration of the experiment began directly challenging our understanding of causality. Based on human logic, there are only two possible explanations. First, particles can foresee the future. They can guess the scientist's next move, thereby knowing whether to behave like a particle or a wave. Second, particles can alter the past. The moment the detector is switched on, the particle retroactively corrects its prior behavior, turning from a wave to a particle or vice versa. Either way, it appears our act of observation can somehow affect reality. But the game of hide-and-seek wasn't over. Scientists decided to push the experiment into the realm of the truly bizarre. What if we first tag the particle to see which slit it went through, but then scramble the data so that we ultimately can't know which slit it took? Will the particle create an interference pattern upon hitting the screen? This is the quantum eraser experiment, where what's being erased is the quantum's path information. Let's stick with photons. Photons have a spin direction. They can spin clockwise or counterclockwise. Suppose we install tagging devices at the slits. A photon passes through the left slit. It's tagged to spin clockwise. If it goes through the right, counterclockwise. We then install a receiver on the screen that reads the spin direction, naturally telling us exactly which slit each photon passed through, right? If we do this, we find that no interference fringes appear, just two bright bands, because the photon's paths were exposed. Now, what if I add another device right before the photon hits the screen, forcing all photons to spin clockwise? This means we no longer have any way of knowing which slit they came from. You can probably guess the result. The interference fringes reappear. It's absolute ghostly behavior. Unsatisfied, scientists attempted an even more diabolical version in 1999, the delayed choice quantum eraser experiment, combining delayed choice with quantum erasure. To put it simply, after a photon passes through the double slits, is split in two, converted into a pair of entangled lower frequency photons, A and B. Photon A heads toward the screen, and we don't look at its state. Photon B heads toward a detector, meaning we can see B's state. Because they are entangled, observing B tells us the state of A. If we do just this, no interference fringes appear on the screen. Then, the scientists split B as well into B1 and B2 and built a maze. Detectors were placed on some paths, and the probabilities of B's descendants taking different paths varied. Let's ignore the nitty-gritty and focus on two conclusions. First, as long as we can use B's descendants to 100% accurately deduce A's path, E will not produce an interference pattern on the screen. As long as we cannot be absolutely certain of A's path, the interference pattern will appear. Second, remember that complex maze scientists built for B and its descendants? The time it takes for B to pass through the maze can be later than the time A hits the screen. Even if that maze were a light year away, it wouldn't matter. Year after A hits the screen, B could finally pass through the maze. When we check the results, it remains the same. It's as if B sends a message back through time to A year later. Hey, I've arrived. Don't worry, they aren't watching you. And A replies, got it. I'll go ahead and interfere then. This deals an even more direct blow to causality. The chronological order of cause and effect might not matter. At least in the microscopic world, it is entirely possible for the effect to precede the cause. If we scale this up to the macroscopic world, we might envision two different futures for humanity, one dark and one bright. The dark vision is that everything in the universe and every personal experience we have might be entirely predetermined. Billions of light years away, an event might have just occurred that will trigger the emergence of human civilization. Or perhaps an event has already happened that will lead to our ultimate demise. Only we have no way of detecting it yet. A fully predetermined world might be running according to a pre-written program. We might just be lines of code or pawns on a board. We appear to have free will, yet still feel swept along by fate. That is the power of the program. The bright vision is that our consciousness can genuinely influence the reality we observe. The world can perceive our intentions and manifest corresponding states for us. Just as with our observation of microscopic particles. Feynman said that whether a particle exhibits wave or particle properties depends solely on how you observe it. This mirrors our own lives. If your shoe breaks and you're forced to walk barefoot on a gravel road, you might feel its sheer torture. But if you're walking on a reflexology footmat, you'd think, hey, the healing is working. Oh, I feel warm and energized. Therefore, consciousness dictates the material world. I suddenly understand why some self-help gurus appropriate quantum mechanics to make their points. So, dear readers, which vision do you believe in, the dark or the bright? Quantum mechanics has perpetually baffled scientists, challenging everything humanity knows about time, causality, determinism, and consciousness. Speaking of consciousness, I'll throw in a bonus egg for you. Observation by consciousness itself. The double-slit experiment is like a blockbuster franchise, with scientists constantly developing spin-offs. We already know that observation collapses the particle's interference pattern. Doesn't matter if this observation is done by directly looking through an instrument, or via measurement and deduction. So, some scientists had a bold idea. What if we used human consciousness to observe the double-slit experiment? What would happen? This time, the experimenter wasn't a physicist, but a psychologist. Dean Radin, chief scientist at the Institute of Noetic Sciences in the US. Radin researches parapsychology, fields like consciousness and mind-body-spirit connections. He has worked in this field for over 30 years. Let's look at how he conducted the experiment. He recruited 137 people. Some were experienced meditators capable of entering a meditative state quickly. Others had little to no meditation experience. Radin separated these two groups, further divided them into smaller teams, and conducted 254 trials. In each trial, a few people would sit in a quiet room and meditate, while a double-slit experimental apparatus was set up in the corner. The researchers would instruct the meditators, now, focus your attention on the double-slit apparatus. About 30 seconds later, now withdraw your attention. This was repeated 40 times per session. Naturally, Radin also conducted 254 control trials without any meditators present. What did they find? When the meditators focused their minds on the double slits, the spectral power of the interference pattern decreased. What does that mean? It means the interference pattern became less pronounced. When they withdrew their attention, the interference pattern became relatively clearer, and the spectral power was stronger. Moreover, the effect of consciousness on the interference pattern was significantly more pronounced among experienced meditators than among those who rarely meditated. The implications of this finding are truly explosive. Essentially provides direct evidence that consciousness affects the physical realm. So, why didn't this experiment make global headlines? Because the scientific community adopted a cautious stance, hoping for further replication and verification. Given that Radin is a psychologist encroaching on physics, and considering his long-term focus on a fringe field, you can probably guess the general consensus among physicists. We can only wait for time to tell. However, I do have a thought to share with you all. In a world where a single particle can pass through two slits simultaneously, a world where all possibilities float in space-time and only collapse into certainty upon your observation, there's really only one truth. Perhaps possibility itself is the truth.